Both vectors and scalars have specific units designed by System International. For example, for time it's seconds, length meters, mass kilograms, force Newton, velocity meters per second. But how do we represent these quantities visually on a piece of paper? Do we draw a clock for time, a ruler for length, particles for mass, or a car for velocity? Drawing images might be cumbersome, so we represent these quantities using lines to show both scalar and vector quantities. In case of scalar, the length of that line corresponds to the magnitude of that particular quantity. If the quantity has high magnitude, then the length of that line representing that quantity will also be greater. A distance of 10 centimeters will have a greater length compared to a distance of 5 centimeters if same scale is used for both quantities. The same analogy applies to vectors. Magnitude of vector quantity is represented by the length of the line. Greater the magnitude, greater the length. However, there is one key difference. As the lines are vector quantities, they must also have a specific direction, which is shown by an arrowhead. This arrow shows the direction in which the vector quantity is either moving or being applied on an object itself. Suppose you have an iPhone 11 Pro and you get another one. How many iPhones do you have now? Well, this should be easy. You had one, now you have another one. So 1 plus 1 equals to 2 iPhones. Simple arithmetic addition. Now consider another scenario. You go from your home to Disney. The distance between your home and Disney is 10 kilometers. What is the total distance you cover moving from your house to Disney and on your way back to your home? Now distance one way is 10 kilometers and you cover twice this distance, once going towards Disney and another when coming back from Disney. So the total distance is 10 plus 10 equals to 20 kilometers. Key thing to remember is that distance is a scalar quantity. So scalar quantities can be added by simply adding their magnitude. In other words, through arithmetic addition. We have Pikachu here. He has only one apple. And he eats that apple. Is there any apple left? Well, no. He had one, and now that one is gone. So 1 minus 1 equals 0. Simple arithmetic subtraction. Let's consider another scenario. You had an apple of mass 500 grams. You eat 450 grams of it. I know it's a rather specific amount, but let's just continue with this example. So after you eat 450 grams of apple, what mass of apple is left? Well, you had 500, you ate 450, so you should have 50 grams left, which is 500 minus 450. We basically subtracted the two quantities. Keep in mind that mass is a scalar quantity. Therefore, scalar quantities can be subtracted through simple arithmetic subtraction. In case of vectors, we have an additional consideration to keep in mind, and that is the direction of those vectors. The onus to add or subtract certain vectors lies squarely on the direction of those particular vectors. If vectors are in the same direction as in the case below, the resultant will be the sum of the two vectors and will also be in the same direction. In the case below, two forces due east of 10 Newton each are striking an object. What will be the resultant force by which the object moves? It will be 20 Newton, 10 plus 10. Those forces are added because they're in the same direction. So when vectors are in the same direction, vector addition will occur. Conversely, if the vectors are in opposite direction, the resultant will be equal to the difference of the two vectors. The direction of resultant will be the direction of larger vector. In case below, two forces of 10 Newton each are striking an object, but in the opposite direction. In which direction will the object move? As the forces are of equal magnitude but opposite direction, the resultant will be 0. 10 minus 10 equals 0. However, if the force due east was 20 Newton, then the resultant will be 10 Newton, 20 minus 10. And the direction of this resultant will be the direction of the larger force. In other words, towards east. So in case of opposite direction, vector subtraction occurs. We discussed cases in which vector quantities are either in the same direction or in the opposite direction. But what if the vectors were neither in the same direction nor in the opposite direction? Should we just leave them? Let's visualize this problem first. We have two forces acting on an object, force 1 due east and force 2 due south. Both of these forces are not in same direction. One is due east and the other in south. Similarly, they are also not in the opposite direction. It's not like one is due north and the other due south, or one due east and other due west. In such cases, we add vector quantities through use of two methods: vector triangle method, also known as head-to-tail method, and parallelogram method. Before we move on, let's clarify what I mean by head or tail in case of a vector. We have discussed that we can represent a vector using a line with an arrowhead. In this case, the arrowhead represents the head of a vector, and the line before that represents the tail of a vector. In vector triangle method, you create a right angle triangle by joining the two vectors. The hypotenuse or the largest length represents the resultant of the two vectors. In this case, two forces 20 Newton and 10 Newton act on an object due east and south. Let's add them using vector triangle method. We do this by joining the head of the first vector with the tail of the second vector. The first thing in this method is to determine the scale for drawing the lines. Forces and velocity are invisible terms. You can't just see them with your eye, but you can experience their effects. Force will push or pull an object in a certain direction, while velocity will move the object in a certain direction. To represent these quantities in a two-dimensional space, we use a line with appropriate scale through ratio method. On our scale, 10 Newton is represented by 1 centimeters. So a force of 20 Newton will yield a length of 2 centimeters, while a force of 10 Newton will yield a length of 1 centimeter. After determining the length, we join the head of the first with the tail of the second. This gives us two sides of a right angle triangle. We complete the triangle by drawing the third side. In this case, the third side, which is also the hypotenuse, represents the resultant of the two forces, force 1 and force 2. It is important to note the direction of this resultant. Its head joins the head of one vector and its tail joins the tail of the other vector. We can draw the vector triangle slightly differently as well by changing the position of the vector due south. If we join the head of this vector with the tail of the other vector, we can still create the vector triangle. The resultant in this case is the same as the resultant of our first case in terms of both length and direction. The head of this resultant joins the head of one vector and its tail joins the tail of the other vector. Now let's move to the parallelogram method. This states that if two vectors represent the sides of a parallelogram, then its diagonal is the resultant of those two vectors. In summary, in this method, we draw a parallelogram and then determine the length of its diagonal, which is also the resultant. Before we move further, what is a parallelogram? It's a four-sided figure in which opposite sides are both parallel and equal. Of these four images, which one is a parallelogram? Let's check each one individually. Figure A has four sides. The opposite sides are equal and parallel, so A is a parallelogram. In figure B, there are four sides and opposite sides equal and parallel, so B is also a parallelogram. Figure C is a square. Its opposite sides are also equal and parallel, so it's also a parallelogram. Figure D is a rectangle. Its opposite sides are also equal and parallel, so it is also a parallelogram. So essentially, all of them are parallelograms. In subsequent sections, we will follow the steps needed to create a parallelogram. Note that parallelogram method is used for vector addition when vectors are neither in the same direction nor in opposite direction. Vectors are in the same direction if the head, in other words arrow, of those vectors point towards the same direction. They are in the opposite direction if the arrows or heads of those vectors point in the opposite direction or path. If the two vectors are at an angle to one another, in this case it is 90, but it can be any angle other than 90. They are neither in the same direction nor in the opposite direction. The scale you use to represent vector quantities must be reasonable. It must not be too big, otherwise the image will be too big to draw. And neither it must be too small, because then it might not be legible. You will use ratio method to determine the exact lengths of particular vector quantities. The key instruments required are compass, ruler, protractor, and a pencil. First, we have to finalize the scale, which we will use to represent the vector quantities. In our case, two forces of 20 and 10 Newton act on an object respectively. The scale we are using is such that 10 Newton equals to 1 centimeter on paper. Therefore, from ratio method, force of 20 Newton will have the length of 2 centimeter and a force of 10 Newton will have a length of 1 centimeter. Next, we mark a point O. This point is our reference point from where we will draw our parallelogram. At O, we draw two perpendicular bisectors using protractor. At 90 degrees, we draw a straight line, and then at 180 degrees, we draw another line, thereby creating a cross. These perpendicular bisectors are drawn at 90 and 180 degrees. They are essentially our x and y axis. Next, we use our compass to draw two arcs the length of our vector quantities. In our case, force 1 was due east and its length 2 centimeters. So by stretching the compass by 2 centimeter using scale, we place the compass at O and draw an arc 2 centimeter from O and then connect that arc with a line to point O. This line represents our force of 2 centimeter. The point at which this arc intersects the x-axis is labeled as A. The other force, force 2, was due south and its length through the scale was 1 centimeter. So we stretch our compass to length of 1 centimeter using the scale and then draw an arc at a distance of 1 centimeter away from point O. Draw a line up to the arc to represent force 2. This line should be of 1 centimeter. The point at which this arc cuts the y-axis is labeled as B. Now that we have two sides of a parallelogram, let us pause for a minute. Note that unlike vector triangle method, in this method the head of both vectors point in different direction, but they are joined together by the tails at point O. But what is a parallelogram? We know that parallelogram has four sides. So we need to draw two opposite but equal sides to complete the parallelogram. The side opposite to force 2 must be of 1 centimeter, while side opposite to force 1 must be 2 centimeters. In order to complete our parallelogram, we will now draw the remaining two sides. To do this, we will first stretch our compass to 1 centimeter and place it at point A. Then we will draw an arc 1 centimeter away from point A. This is the side opposite to the length of force 2, and as this is a parallelogram, it should be equal. Then, using scale, we adjust our compass to a length of 2 centimeter and draw an arc from point B 2 centimeters away. This side is opposite to the length force 1 and must be of equal value, in other words 2 centimeter. The point at which these two arcs intersect is marked as point D. We then draw lines to connect point D to point A and B respectively. This completes our parallelogram, a four-sided figure where opposite sides are equal and parallel. Next step is to draw the resultant length. You draw a line from where the tails of the vectors meet to the point D. In our case, it is from our point O to our point D. the point of intersection of the two arcs. This yellow line is our resultant length, which we can measure through the use of a ruler. Make sure to draw an arrow to show the direction of this resultant. We have painstakingly calculated the resultant length, but unfortunately this is not our final answer. We must convert this length into appropriate vector quantity using our original scale. In this case, our scale was 1 centimeter representing 10 Newton. Let's assume that our resultant length is 4 centimeter. What is the value of the resultant force of the two vectors? We know that 10 Newton is represented by 1 centimeter. So 4 centimeter represents, let's assume, an unknown or x newtons. We can simply find the value by cross multiplying, and that is 40 Newton. This is ratio method, and it will be assumed that you are comfortable with it. After all, it's not a maths class. Sometimes the question requires you to mention the direction of this resultant vector. The direction of this resultant vector is the angle of resultant length with either x-axis or y-axis. It is measured in degrees through protractor instrument. So you will simply place protractor at point O and determine the angle of resultant yellow line with either the x-axis or with the y-axis. In this case, the red angle is the angle with x-axis and the blue angle is the angle with the y-axis. This was a comprehensive overview of the parallelogram method. It might seem daunting at first, so many steps, so little time. But with practice of past paper questions, you will find that these steps are relatively easier and manageable. Also, the range of questions and scenarios are limited, in such that most of the questions have been repeated periodically in your past papers. So just get a grip of the basic idea of these questions and you will eventually learn how to deal with them.